Within our solar system, there are two worlds where rock and ice and chilling winds rule bleak landscapes. Once, both were warmer, and rivers wandered through valleys where today the highest temperatures just barely pass the melting point of liquid water. In one of them, winter lasts 4 months of freezing darkness. Upon the other, winter has lasted 3 billion years or more. Two lands where life once had a chance to flourish. Two lands where, at first, it seems no trace of life remains. But one of them is rich in hidden life, though alien and strange. And the other is a planet we yearn to explore with the wisdom gained from discoveries about how life can endure amidst adversity. This is the story of Antarctica and Mars, and a courageous and astonishing search for life that has taken humans deep below the icy crust of lakes near Earth's South Pole and given us tools to search for ancient life on the planet Mars. The Antarctic winter ends. 4 months of utter darkness are about to be followed by 4 months of endless summer. Even in summer, this can be a forbidding place of cruel winds and bone-chilling temperatures. Antarctica is a harsh but beautiful land, full of contradictions. On a continent almost completely covered by ice and snow as much as 3 miles thick, there exists an exposed barren region that more resembles the surface of the planet Mars than any other place on Earth. These are the dry valleys of Antarctica. Rocky, wind-carved wastelands that are some of the driest places on Earth. Even the Gobi Desert has more moisture. Scattered across these dry valleys are bodies of seals lost or trapped here long ago that are mummified like Egyptian pharaohs. In this bizarre place, the remains do not decay, but are slowly eroded by the sandblasting effect of wind and sediment, carving them into strange, eerie shapes, just as it does to the rocks and boulders that litter the landscape around them. Carbon dating has shown that some of these freeze-dried carcasses are over 6,000 years old. But in each Antarctic summer, in one of nature's fertile ironies, a dry desert valley can become an oasis. The warmest days are in late December and early January. Sometimes temperatures remain above freezing for days in a row, and a continent of ice begins to change. For just these few days, running water can exist. And water, on Earth, is essential for any kind of life. But what kind of life could there be in such an inhospitable climate? The rare liquid water slips over the dry soil and resupplies lakes that dot some of the dry valleys. These strange lakes are the closest you can get to the South Pole and still find liquid water. And in these oases in a frozen desert, scientists are beginning a search that will take them back in time and help humans prepare for the quest for life on other worlds. October, summer in Antarctica. A team of scientists and explorers, biologists and planetary geologists, returns to the dry valleys to continue their studies of life amid some of the most extreme conditions on Earth. The researchers were sponsored by the Division of Polar Programs of the National Science Foundation. Some of the scientists work for NASA. Their purpose here is to prepare for a time when robotic and then human explorers will travel to Mars and beyond in search of extraterrestrial life. The Dry Valley Lakes were first seen during R.F. Scott's Discovery expedition of 1901. But for over half a century, their strange depths were unexplored. Only in 1978 did researchers find a way to penetrate the year-round ice. When they did, they discovered something unexpected and mysterious. Researcher Dale Anderson prepares to dive below the ice. He gets assistance from the other team members in rigging the bulky dry suit.
Put your knee back, elbow back against it. Okay.
Diving below the Antarctic ice is physically stressful and potentially dangerous. Anderson's progress will be carefully monitored on the surface by two other experienced ice divers, team leader George Simmons and Robert Wharton of the Desert Research Institute. During their stay in the Antarctic, each researcher will in turn enter the frigid waters below the ice. Each will share the reward of a first-hand glimpse of this unique world, and each will share the risks. In addition to the human divers, a remotely operated vehicle, or ROV, was used. The ROV carried a television camera beneath the ice. The pictures you are about to see come from both the human and the robot cameraman. This is what they saw. A strangely beautiful world where life does not run by our accustomed rules. These unique video images provide for the first time a view of the underwater world inside the Dry Valley Lakes, which until now have only been seen by members of the expedition. Below the ice, the water temperature remains just above freezing all year round. As each summer's runoff enters the lake, it brings with it dissolved gases and nutrients, which are then trapped under the perennial ice. In the coldest continent on Earth, the ice turns the lakes into greenhouses and bottles up nutrients and gases for a kind of microscopic life, which, though small, lets us humans transcend time. Living fossils that show us something of the early years of Earth. Each year, some ice evaporates from the top of the lake and 3 feet of new ice freezes down below. This combination of ice and liquid water creates a unique ecosystem that allows life not just to survive, but to flourish.
out of the way. This tank's over here. Roll over. No, just roll. I got you.
George Simmons, a biologist from Virginia Tech, was the first person to guess there might be living creatures deep down under the ice. Other researchers insisted that nothing could live down there. But then, he made his first dive.
I was the first person to go through the ice cap in order to examine the bottom. Well, at first, as I was descending through the water column and looking at the bottom, at first, I guess I was very depressed that it looked as though there was nothing at all growing on the bottom. We had been assured a few days before that absolutely nothing could grow beneath these thick ice covers. The bottoms of the lake were essentially sterile. But upon landing on the bottom, I realized that the entire bottom quaked around me, much like landing on a big bowl of Jell-O. I stuck my hand into the sediments and realized that I was holding a very, very thick microbial mat community. And as I sat there on the bottom, looking at this material, I realized that as far as I could see, which was 20 or 30 feet around me at the time, that as far as I could see, the bottom of the lake was covered by a very rich, luxuriant carpet of microbial mat.
Simmons calls the dive holes time tubes, and in our imagination, they can take us back 4.5 billion years to a time when our solar system was young and life on Earth was soon to begin. Out of a spinning cloud of gas and dust, gravity collected a clump of matter which one day sparked alive, the star we call our sun. Earth and Mars, the third and fourth planets from the sun, condensed as a mix of rock and gas and became neither fiery cinder nor icy gas planets, but something in between. Much of their early history must have been rather similar, but then something happened. Today, as we begin to recognize the climate changes our Earth seems to be undergoing, perhaps there are important lessons in what happened long ago to our sister world. At first, all the planets were battered by storms of asteroids, leaving craters we can still see on the moon. But soon, on Earth, internal heat began to drive earthquakes, build volcanoes and mountains and continents. Craters disappeared amid the rains and seas. And somehow, somewhere, life began. And on Mars? As yet, we simply don't know. But there are majestic clues to a very interesting past. On Mars, there are mighty volcanoes like Olympus Mons, 3 times higher than Mount Everest, which once upon a time must have spewed out huge clouds of lava and gas. There is a great rift valley named Mariner Valley after the American spacecraft that discovered it, that would stretch from New York to Los Angeles and is 3 times deeper than Arizona's Grand Canyon. Our robotic spacecraft have shown us evidence of rivers and huge floods that must once have gushed across the land. But was Mars really more Earth-like in those early days? Did life begin there as it did here? Why would an answer be so important? Carl Sagan, a longtime proponent of the search for life beyond Earth.
We don't know what else is possible. We don't know what other kinds of life there could be. We are ignorant. Find any kind of life elsewhere, and that ignorance is removed. Biology becomes a kind of cosmic science. And right now it's a provincial science. It's not any fault of the biologists. They happen to be stuck on this one planet.
Steve Squires is a planetary geologist from Cornell University who has worked in the Antarctic.
Because if it happened, it's so important. It would completely reshape our thinking about our place in the universe, to know that on some other planet that life originated. It would be, if we found it, the most important scientific discovery ever made. And beyond that, if conditions on early Mars were fairly Earth-like, as we think they may have been, and life did not originate, then we have to understand why. It says something profound about the conditions that are necessary for life to come about. So whether the answer is yes or no, it's still an important question.
There are plans for further Soviet and American robotic missions to Mars, but there will be no human expeditions before at least the year 2000. Is there any other way to study the red planet? Can we somehow jump millions of miles and billions of years?
Suppose you were to take a walk on the surface of Mars. What would it look like? Well, in a lot of places, it might look very much like what you see right here. The Antarctic dry valleys constitute just about the most Mars-like environment anywhere on the Earth. The climate here is similar to the Martian climate, and the physical processes that are shaping the surface here are very similar to some of the processes shaping the surface of Mars. What this means is that the dry valleys are a very good place for us to test some of the hypotheses that we have concerning what's going on the Martian surface. And it may also be a very good place to test some of the techniques and some of the equipment that we might want to use to study the surface of Mars at some point in the future.
Chris McKay is an exobiologist helping plan Mars missions at NASA's Ames Research Center.
Early life on Earth was closely tied to the environment of the early Earth. Life is, in many ways, a planetary phenomenon. One of the goals of NASA is to understand the relationship between the physical and chemical evolution of the solar system, the formation of planets, and how this relates to the appearance of life. In this respect, besides the Earth, Mars is one of the most interesting planets for study.
Most of our knowledge about Mars comes from the twin Viking missions launched in 1975. Viking 1 and 2 arrived at Mars in mid-1976. Each orbiter released a lander, which floated down to the Martian surface.
Viking missions to Mars in 1976 seemed to show that there was no life on the planet now. However, those same missions showed ample evidence that billions of years ago there was water flowing on the surface of Mars.
The visual evidence seems to indicate there could have been enough water to have covered Mars' entire surface with as little as a few feet of water to as much as several hundred feet. Today, what water was there has now dried up almost completely.
Water is the quintessence of life. Where there is water, there is the possibility that there is life. That led us to question, could there have been life on the early Mars? And if so, where would we go to look for that, for evidences of that past life?
It's in these oldest places where we see evidence that Mars was once a warmer and wetter place than it is today. What we see are what look like ancient river systems that have been eroded into the Martian surface that are telling us that there was once a substantial amount of liquid water present near the surface of Mars. Now, there's also a lot of evidence on Mars for tectonic activity. That is, geologic activity that has produced faulting, that has produced large canyon systems that stretch for great distances across the Martian surface. What we believe is that these canyon systems at one point were filled with liquid water, producing what would have been extremely large lakes. The lakes probably were covered with ice, very much like the lakes here in the dry valleys. Now, the lakes are not present today, but what we do see today are thick sequences of layered sedimentary deposits that we believe were laid down in these ancient Martian lakes.
High-resolution Viking images show what appear to be horizontal layers of sediments continuing for many miles. Their shape and size convince many scientists that these rocks and sediments were most likely laid down in standing water, like a lake, and over a long period of time. Some scientists think these bodies of water could have been as large as America's Great Lakes. Geologic activity may have sustained enough heat to have left liquid water in these canyon lakes, even as Mars slid into an icy planetary deep freeze. If life ever began on Mars, these lakes may have been the sites of its last stand against the onset of cosmic winter. What was happening on Earth at this time? Just as on Mars, there were volcanoes, water, and, at least on Earth, very soon after the surface cooled, the beginnings of life. In 4 billion-year-old rocks, just 500 million years after Earth formed, we can find traces of microorganisms whose bodies mingled with rock to become the fossil sediments known as stromatolites. These are similar to the communities of organisms Simmons and his team found beneath the Antarctic ice, living stromatolites.
The earliest record of life on Earth are the stromatolites, which are 3.5 billion years old. These stromatolites represent an already fair degree of biological sophistication, and that indicates that life must have evolved earlier and undergone a fair degree of biological evolution. The events of this early period, though, are obscured on Earth because of the extensive weathering and activity due to volcanism and plate tectonics and other such things. How then can we get a picture of this earliest stage of life? The answer to that question may be the planet Mars. If Mars did indeed have a warm climate period billions of years ago, and if life did indeed evolve on that planet, then there's a better chance than the record of the early evolution of life is preserved on Mars and that we can find it there. Because on Mars, 60% of the surface dates back to over 3.5 billion years ago and has been unaltered by essentially plate tectonics and volcanism. Mars may hold the best record of the events in the early evolution of life.
It would be a fine irony if Mars, which may well be lifeless today, is still the best library of the early history of life in our solar system. Whatever its past, Mars today has conditions that are very hostile to life. Temperatures range from minus 193 degrees Fahrenheit to 68 degrees Fahrenheit. Its present thin atmosphere lacks ozone, allowing Mars to be bombarded with ultraviolet light, which destroys the molecules of life. But in its first billion years, Mars could have been more clement, and if life started on Mars as early as it did on Earth, there may have been time enough to leave evidence in fossils, if we can find ways of understanding it. McKay and colleagues believe the Antarctic lakes are time machines that can help them understand what might have happened on Mars.
By studying these lakes, we hope to be able to relate the physical and biological processes going on in the lake with what is recorded in the sediments at the bottom of this lake. If we can make that transformation between what's going on in the lake and what is recorded in the sediments, then when we go to Mars and bring back sediments from those lakes, we might be able to work backwards, if you will, and understand what the environment and possible biology was in those Martian lakes billions of years ago.
This has a very interesting connection with Mars, because 3.5 billion years ago on Mars is the epoch, apparently, when the climate was much more benign, when liquid water was flowing through the channels, when there may have been standing lakes and other bodies of liquid water, when the pressures and temperatures were higher. That's a good time to think of life on Mars. But you might ask, is there enough time in the first billion years of Martian history for life to evolve, especially into forms big enough to see? And here we have on the Earth An example of that, and the answer here at least, is yes. Life, including big life, colonial collections of microorganisms, was able to evolve in the first billion years of Earth history, probably even quicker than that, from, presumably, no life at all. If it could happen here, it could happen on Mars. And so it's a distinct encouragement to those of us who wish to look for fossil forms on Mars.
If life began on Mars, just perhaps it might still exist, as some Soviet researchers hope, in long-term hibernation, in oases over tectonic hotspots, or deep below the permafrost. If life is now extinct, its record in the rocks may be frozen in time, mummified, with no recent storms or floods to destroy its mute testimony. For now, as we wait for future missions to return to Mars, we can try to answer some of these questions in Antarctica. Ice covers almost all of Antarctica's 5.4 million square miles. On average, it towers about 7,000 feet above sea level. It has 90% of all the ice in the world and holds nearly 3/4 of all the world's fresh water. Inland, mighty mountain ranges divide the continent, and the mean annual temperature is -70 degrees Fahrenheit. Antarctica is Earth's coldest continent, with a world record low of -128.6 degrees Fahrenheit. "200 million years ago, conditions were very different. Then, Antarctica was joined to South America, Africa, Australia, and India in a single large continent, and there was dense vegetation and many animals. Today, only fossils and beds of coal made from those forests of long ago testify to Antarctica's past. Sea ice, up to 10 feet thick, circles the continent year-round, stretching as far as 1,000 miles out into the 3 oceans that surround Antarctica. These coasts are the windiest places in the world, with gusts of up to 200 miles per hour. McMurdo Station on Ross Island is the main U.S. scientific research base in Antarctica. The base is built on lava from nearby Mount Erebus, still an active volcano. It's the staging area and supply base for expeditions into the interior. Summer in the Southern Hemisphere, October through January, is the season when most U.S. scientists come to Antarctica, flying by way of New Zealand and on to McMurdo in Air Force C-141 cargo planes. In winter at McMurdo, there will be only about 135 people, but now, in summer, the population will swell the American contingent to nearly 900. The best way to travel in Antarctica is by helicopter. Traveling at up to 120 knots, each helo can carry 6 to 8 people, or up to 1,600 pounds of equipment. The helo pilots are a hardy bunch, careful and always willing to lend a hand with the research. Antarctica offers these pilots some of the most spectacular flying on Earth. But as everywhere in Antarctica, there's always a chance for disaster. During the long months out in the field, the helo is the only physical link to civilization back in McMurdo. But sometimes the weather is so bad, the helos can't fly for up to a week. Despite the hardships and the dangers, Most people who have worked in Antarctica are captivated by the land and its uniqueness.
One of the things I remember best is the feeling when you first go out to the dry valleys, your first trip out. Because you're in McMurdo. McMurdo Station is this big, noisy, crowded, Navy-based kind of place. It's a great place if you like mud and Quonset huts. And you're waiting and you're waiting and you're waiting for the helicopter. Then finally the big day comes and you've got your flight. You get on the helicopter, you put the helmet on, you get in the helo, rotors start up, it's noisy, you're talking, you're yelling to the crew chief, you're talking to the pilot over the radio or the intercom, and things are going a mile a minute. You take off, go zooming out to the dry valleys. Things happen really fast. You get out there, they drop a smoke grenade to see which way the wind is blowing. There's rotors flying everywhere, and there's wind, and you sit down, and then you have to unload, and the crew chief is yelling, and you're hauling stuff up and running back and forth and trying to keep the rotors from hitting you. And it's just slightly organized chaos. And then the helo, the pilot waves, and it flies away, and it's just quiet. And there's you, and there's the rocks, and there's the wind, and it's like all of a sudden you're on another planet. And the transition from just the technology and the noise and you know, we got to get there, and then all of a sudden, there you are. And you're facing the next 6 weeks just doing what you want to do. And that first feeling of, boy, I'm really someplace different is great. That's one of the things that I remember the best.
Team leader George Simmons feels it takes a special kind of individual to work successfully in these conditions.
When you're in a remote situation like this, all of the equipment that is used essentially has to be man-hauled from one research site to the next. This is true regardless of the size of the equipment, the weight of the equipment, or the sensitivity of the equipment. In our particular case, in moving our diving operation from one research dive hole to the next, it may take 2 to 3 hours of several people working and hauling equipment, sometimes as much as a half a mile across the broken ice surface of the lake. Sometimes, particularly during this time of the year, it can be very dangerous in the sense that the ice can give way with the person pulling the sled. If the load's heavy, they could be crushed by the sled. They could fall through the surface of the ice, and while there's no risk to drowning, there is risk to breaking a limb or certainly tearing tendons or ligaments, in which case the person would have to be evacuated for medical treatment.
But Simmons thinks mental attitudes can be as important as physical performance. For the research season is a time of perpetual day, and the isolation of the field camps takes away normal cues about when to work and when to rest.
But here in a remote camp like this, all of those cues which tend to regulate our life are gone. And so the success of a particular research project depends upon the perseverance of the individual scientist. So the scientist himself has to set up his own cues, a very strict, rigorous daily schedule that must be adhered to in order for the objectives of that particular project to be completed on schedule. Oftentimes, with many people who come into an area like this and experiencing the lack of these cues that regulate their daily life, they tend to sort of slip into what you might consider to be a mental lackadaisical attitude, in which they sort of put off until tomorrow or the next day what should be done today. At least on our team, we sort of have a philosophical saying, and that is that seconds are worth minutes, minutes are worth hours, hours are worth days, and days are worth weeks.
About 60 miles west of McMurdo Station is Taylor Valley. And in the middle of one of Antarctica's strange dry valleys is Lake Hoare, one of the dozen lakes that are being studied by the NASA NSF team. About 2 miles long and about half a mile wide, Lake Hoare is dammed at one end by the Canada Glacier. At its greatest depth, it's about 100 feet deep, and its average temperature is just about freezing. But getting to Antarctica, flying by helo out to the dry valley, setting up camp and trekking with equipment out to the study site at the lake is only the beginning. With the ice on Lake Hoare 10 to 18 feet thick, breaking through to the water to begin the dive is a 2-day exercise in itself. At first, Simmons thought about using dynamite to break up the ice. But then he realized this was not the most neighborly way to study a living community of microorganisms, and it would pollute the lake as well. Then Simmons thought of chainsaws, which the researchers used to cut out blocks of lake ice to study its composition. As Simmons said, the first 14 feet, no problem. But who would be the brave soul who would cut away the last few inches and release a torrent of icy water? Eventually, one of his colleagues came up with a plan, and Simmons prepared to put the unique method to work. A generator heats an antifreeze solution and then pumps it through a coil made of copper tubing. The coil, about 4 feet across, takes as much as 2 days to slowly melt its way through the ice, creating a smooth 18-foot deep vertical shaft down to the liquid water below. Now the real work can begin. Steve Squires expresses the feelings of danger and delight experienced by all the divers entering this underwater world.
Well, your first impression as you're going down the dive hole, you talk about it being a hole, and when you look at it from the top, it looks like a hole, but when you're going down, I mean, this thing is 3.5 meters deep. It's like going through a tunnel. And it's this beautiful glacial shade of blue. It's just this lovely blue. And there's the bubbles, and it's like being in it's like glass or something. It's like being in a cathedral. It's gorgeous.
Down 818. What's your air pressure?
When you first get into the water column, all you see is blue. You can look up and you can see the dive hole, and it's this big, beautiful white tunnel going up to the sky. But then once you get down to the bottom, you slowly settle down, and you get down on the bottom, and then you see the mat. You see the algal mat. And in some places, it's just, you've got these little mounds, this little bit of topography. But there are other places, the mat produces a lot of oxygen, and it tends to lift the mat up off the bottom. The bubbles do it. And in other places, huge chunks of mat, 3, 4, 10 feet across, will rip up from the bottom, and they'll be standing up like pillars or something from these weird shapes. And it's a very otherworldly sort of environment. It's not like anything that you see anywhere else. And when you first get down to the bottom, it's really the shapes and the upripped mat that, more than anything else, catch your attention.
Only 1% of the sun's energy makes it through the thick ice cover, and even less sunlight makes it down to the very bottom of the lake. The year-round ice cover also concentrates gases in the water in a very different way from any other lakes around the world. The organisms that live here have had to adapt to extremely high oxygen levels, as much as 4 times greater than usual, a level that would normally be poisonous. In the deeper reaches of the lakes, the microbial communities are fairly uniform, flat, horizontal, and featureless. But in the shallower reaches, we are confronted by an eerier world, where strange forms reach towards the surface. The supersaturated concentration of gases in the water causes bubbles to form in and under the algae, deforming the delicate structure of the mat. Large mounds loom in the darkness. Hollow domes covering pockets of gas leave loose folds and hanging flaps as they tear apart. In other places, portions of bubble-filled mat become buoyant, forming soaring columns of algae. Overhead, bubble channels mark the migration of gases through the ice, creating beautiful, glittering chandeliers and displaced visions of the starry heavens. Together, they create a surreal underwater world, a world suspended in time and space. The algal mats are everywhere in rich, profuse abandon, beneath the ice in every lake in the dry valleys. Each lake has slightly different kinds of mat, but they all draw calcite, iron, and sulfur out of the water. And as the algae grow and die, they trap sediments and form alternating layers of organic and inorganic matter. This is the first time that the resulting structures, a kind of modern stromatolite, have been discovered growing in such cold, dark water. As we've seen, stromatolites like these were the first telltale sign of life on early Earth.
So life can just barely start get going, I don't know, let's say 4.2, 4.0, 3.9 billion years ago, something like that. And that means that in just a few 100 million years, life went from nowhere to these big stromatolites. That's very fast, and that suggests the origin of life is easy. And if it's easy on the Earth, maybe it's easy on Mars.
The ice on the surface of the lake also has a story to tell. The researchers have to saw it out in order to study its composition, which will provide them with a history of what has been happening to the lake, both its water and the gases that are dissolved in it. Each ice cap records about 15 years of lake history. In the same way, cores taken from the bottom of the lake tell a story of planetary evolution. But these cores let us reach back far longer in time. To geologists like Squires, each core is a book with a 5,000-year-old story to tell, to be read in each layer or strata of the sample.
One of the most basic tools that's used by geologists is the principle of stratigraphy. That is, if you have a sequence of layers of geologic material, the oldest material lies at the bottom of the sequence, and the youngest material lies at the top. So by taking a cross-section or a core through a sequence of layers, you can learn something about the history of the geologic events that have taken place in that location. Now, I've just taken some cores from the bottom of Lake Hoare here, and from it we can deduce a sequence of events in the lake. For example, we can see at the bottom there's a layer of organic material, there's a period in which fine sediments were being deposited, then a period of coarser sedimentation. Here's another organic layer that developed, some very coarse sediments towards the top, and then right at the top very recently, we have a layer of organic material. Now when we go to Mars, we'll be able to do a very similar thing. That is, we can take cores from sedimentary material on Mars, and from that deduce a history of events where the sediments were laid down. For example, we can determine the nature of the sediments that were being deposited. If, for example, there are something like carbonates present, we can learn something about the chemistry of the water in which the deposition was taking place. And finally, if there was ever any biologic activity on Mars, it might be possible in the cores to find fossil evidence of that life.
Mars. Both the Soviet Union and the US have their sights set on the red planet. Dreams of piloted missions are rapidly being transformed from science fiction into engineering concepts. And the hardware that could take humans to Mars and sustain them while there is being researched. Some NASA planners want to place a mock-up of a future Martian base in the Antarctic and leave its inhabitants for over a year. To understand the effects of isolation on small groups of people, and to test and evaluate the emerging technologies which may one day be used by the first explorers of Mars. More immediately, in 1992, America will send the Mars Observer spacecraft to orbit the planet, and Antarctica's interwoven story of water, life, and sediments may help some researchers interpret what they see. On the drawing boards, though not yet approved or funded, is a Mars rover sample return mission, perhaps to be undertaken in coordination with the Soviet Union and other spacefaring nations. Again, NASA's experience in developing equipment in Antarctica will be put to good use. Dr. John Rummel, Exobiology Program Manager for NASA.
Antarctica right now is a key place to develop the techniques, the actual techniques, and indeed potentially the actual instruments to study Mars later on because of its unique dry and cold nature, much like Mars is. The actual Mars environment will represent additional challenges, but we'll have those same people working on those challenges later on, and they'll be able to adapt as a result. In the future, we might also use Antarctica as a place to train astronauts themselves prior to any manned Mars expedition, and actually give them a place on Earth where they can develop the techniques that they would use on a Mars expedition.
The Antarctic research has also given scientists a new understanding of what machines like the ROV can and cannot do, and what humans are best at.
The great thing about the ROV was that it gave us a chance to really explore the lake bottom in detail for long periods of time. It's run by a generator. You can put it down the hole, and you can run it more or less indefinitely until you run out of gas for the generator. So what we would do is we put a dive hole in, and we put the ROV down, and we'd explore with the ROV for hours before we'd ever put a diver in, because diver time on the bottom is very precious. The ROV time was easier. It was a real good tool for us to use. That's fun. Flying the ROV is sort of like playing a terrific video game. You've got this little monitor in front of you that looks like a cross between some kind of arcade game and an F-16 cockpit. You've got these two little joysticks that you move. There's a color video monitor in front that shows you what the ROV is seeing, and you just fly the thing around.
Although when Squires had a chance to explore the bottom of the lakes in person, he discovered things that humans guiding robot eyes might simply have missed.
What I found was that when I had that ROV down the hole and I was flying it around and looking at things, I collected a lot of information. I saw things, but I didn't always understand them. It wasn't until I physically got down into that lake and with my own eyeballs, my own brain, and my own hands, started touching things and pulling things apart. And, you know, the human brain is very good at sort of formulating a hypothesis, testing it, throwing it out, coming up with another one, yes, boom, 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 real fast like that. And you can't do that. You really can't do that nearly as well unless you're in the environment yourself. So it made me really rethink a little bit this issue of human versus unmanned exploration. There are great things you can do with robot spacecraft. Viking, Voyager, they've done marvelous things, and the next step for Mars is definitely an unmanned thing. But I really believe that we're not going to have true understanding, really deep understanding, until we have people there and they can interact with the place. That's just the way humans work.
But it will be perhaps 2 decades before humans get to Mars. And so for now, we can pace the frozen deserts of Antarctica while we design and launch robots to sift the sands of Mars. We can probe icy cracks in deep lake ice and dream about the penetrators that will burrow deep down into Mars permafrost to look for ancient life.
But this time, instead of going to the most boring places we can find on the planet, because those are the safest, we go to places that are relatively safe, but that we have the capability to move around with a robotic vehicle and to pick up rocks and to pick up soil and to bring that stuff back and analyze it in terrestrial laboratories. So the next step is an unmanned robotic vehicle that can walk around on the Martian surface that can bring us back pieces of Mars so we can answer the really tough questions about what the early climate of Mars was, what the details of some of the geochemistry are like. The next step after that, and not until all this has happened, is to send people.
What else can we learn from this trailblazing Antarctic research? For one thing, it has shown us that life can endure and even flourish under what might at first seem unlikely conditions. And that opens our minds to the possibility of life in the harsh climate of the outer solar system, like Jupiter's giant ice-covered moon, Europa.
10 years ago, before Voyager got to Jupiter, we wouldn't have had any reason to suspect that there was liquid water under the crust on Europa. It wasn't until we learned what we learned from Voyager that we began to realize, hey, this might be an interesting place. So as our understanding of the worlds out there evolves, then our perceptions of where are the good places to look change as well.
One lesson is that we're simply too ignorant to make confident assertions about where there is and where there isn't life. We have to be a little more humble and a little more open to the experimental method is the only way of deciding.
The most intriguing results are those that life is much more flexible than we at once assumed. The ability of life to make use of even the most obscure Earth ecosystem areas and niches is something that only the experience in Antarctica has really plumbed to a major degree. Life's ability and tenacity to maintain a foothold wherever it once is established is something that we will count on in our study of Mars, given that the possibility of life having originated on Mars back in an earlier, warmer, wetter period, we'll look for the same sorts of traces of a tenacious life on Mars when we get there.
The Antarctica experience also prompts us to reassess the roles and tasks of robots and of humans in the future exploration of space. Could we have designed machines smart enough to follow hunches, to wonder, as George Simmons did, whether the algae extended out under the thick ice? Would we have programmed machines with sufficient ingenuity and dexterity to melt holes in deep ice, and the mechanical guts to haul heavy loads across dangerous cracks, and then plunge into freezing water? But there are other ways in which Antarctica may point the way. Antarctica is not just a unique physical environment, but also a unique political realm. The Antarctic Treaty, ratified in 1961, commits the signing nations to use the continent only for peaceful purposes. Here, international cooperation is mandated. Many argue that we should adapt the Antarctic Treaty to space and explore the solar system and its resources for all mankind, and leave our warlike nature behind us as we continue outwards to the stars. Looking at what we have achieved in Antarctica, we can dream forward to days when inner space has become outer space. When astronauts float around the icy cores of comets deep in space, instead of glaciers protruding deep down into lakes. We have found that life is more ingenious than we thought, and may still have tricks to play on us humans, on this world, and on the worlds in space our robots and our future explorers will visit. Perhaps one day, as some science fiction writers, and even NASA scientists have said, we will seed the polar caps of Mars with genetically engineered relatives of those same algae who first appeared on Earth and made our sky with the oxygen they breathed out, and gave us humans a chance to thrive, and left us evidence of their presence in stromatolites. Maybe we will send their descendants to Mars to rekindle the evolutionary forces of life and make an Earth-like world on a planet now trapped in a cosmic midwinter. It's called terraforming, and perhaps the algae we encounter in these Antarctic lakes will be part of the microscopic core of bioengineers who will make it happen. And then one day, summer may come back to Mars.